at how the coherence of the Eureka math curriculum is beneficial to students. In this session, we are going to discuss how models that are used in a story of units, which is the K through 5 curriculum, will help students all the way throughout a story of functions, which is the 9 through 12 curriculum. Let's go ahead and use a model to multiply 15 times 13. Now, I am going to set this up in this manner. 10 and 5 and 10 and 3. With an elbow partner, I would like for you to discuss why I drew my model the way that I did. Would anyone like to share their responses? Excellent. That is correct. All that is happening is I wrote an equivalent expression that makes the numbers easier to multiply. A story of units uses area models for multi-digit numbers to teach multiplication algorithms clearly and for understanding. It clarifies the use of the distributive property to generate and record either 2, which is the sum of the layers, here and here, or 4, which is the sum of the areas, partial products, when multiplying multi-digit numbers. In Part A of the Algebra 1 Module 1 task in your participant handout, please fill in this model. When completing this, we're going to start with this 10. 10 times 10 is 100. 10 times 3 is 30. 5 times 10 is 50. And 5 times 3 is 15. Once we have the partial products filled in, then we can add them up, showing that 10 plus 5, which is 15, times 10 plus 3, which is 13, is equal to 100 plus 50 plus 30 plus 15, giving me 195. The work with concrete numbers in a story of units sets the foundation students need for doing work in a story of functions, like when they start to multiply polynomials. In the next example, we're going to use the tabular method instead of the rectangular array. The reason why we use the tabular method is because once you get to more complex numbers, for instance, negative values, you can no longer call this model a rectangular array, because when we're using a rectangular array, we are referring to length. And when we are referring to length, we cannot use negative values. So by simply changing the name of it to a tabular method, or a tabular model, we can use the same concepts to multiply things like polynomials. Now, in your Algebra 1 task in Part B, go ahead and use the tabular method to now multiply x plus 5 times x plus 3. So we start by drawing the model. And we have x plus 5 here, and x plus 3 on this side. That's going to give me x times x, which is x squared, x times 3, which is 3x, 5 times x, which is 5x, and 5 times 3, which is 15. this, what do you notice about the partial products of the diagonals? Excellent. The like units are along the diagonals. Here we have x squared. Here we have the 5x and the 3x, which sum to give us 8x. And then here we have 15. This shows us that x plus 5 times x plus 3 is equal to x squared plus 8x plus 15. What coherence do you notice from part A to part B? Yes. Awesome. So they are now using variables, okay, instead of all numbers, but it's the same process as the rectangular array. Yes? Awesome. Also, you notice that the 10s are simply replaced with x's from part A to part B. So if I were to substitute 10 in for x down here in this expression, x squared plus 8x plus 15, and then simplify, I would end up getting 195 just as I got in part A. We can even take this one step further, and we can use something called the reverse tabular method to help us factor trinomials. In part C, this is exactly what we're going to do. We are going to use the tabular method to factor x squared plus 2x minus 15. Does anyone know where we would want to start there? Great. We're first going to set up our tabular model. Now, so far the only information we know is we know the diagonals to the partial products. For instance, we know that this is going to need to be broken down to multiply to give me x squared. These two are going to have to sum to give me 2x. And this is going to have to multiply to give me negative 15. Now I need to determine how I'm going to find these four unknowns. Well, looking at what we did above, are there any partial products that we can fill in right now? Absolutely. We can fill in the top left box, which is x squared, and we can fill in the bottom right box, which is going to be negative 15. Now, the reason why we cannot fill in these two boxes is why? Yes. Excellent. Because it is going to be the sum of two partial products. So now we need to figure out if there's anything we can do further. Well, looking at this, okay, based off of what we did here, are there any of the two unknowns in the spots above or to the side of the model that we can fill in? Yes, we can fill in the x on the top left and the x on the top right. We know this because the only way to produce x squared is to multiply x times x. Now we need to think about how we are going to find the other two values. Well, based off of what we did here, we know that the number in this box, the lower right-hand box, was found by multiplying the two numbers that we're looking for. That value is negative 15. So, what are some factor pairs that will give me negative 15? Well, we have 1 and 15, 1 and negative 15. We have negative 1 and positive 15. We have positive 3 and negative 5. And we have negative 3 and positive 5. But which of those combinations is going to work for our problem? Well, now we need to take into account that the number here, which is 2x, is going to be the sum of the two numbers that I'm going to find. Well, 15 and 1 will not give you 2. So let's think about 3 and 5. If I took positive 3 and negative 5, would that add to give me positive 2? No. But what if I reversed that and said negative 3 and positive 5? Would that add to give me positive 2? Absolutely. So my two numbers here need to be 5x and negative 3x. So now that I have this filled out, can I find these two values? Sure, right? What times x gives me negative 3x? That's going to be negative 3. And what times x is going to give me 5x? Correct, that is going to be 5. This now shows me that the factored version of x squared plus 2x minus 15 is x minus 3 times x plus 5. This is a very